So we're in the, kind of in the thick of it, like the astronomy of astronomy. And what we're going to do is we're going to construct the Hertzsprung-Russell diagram, or the HR diagram. I'll probably use its full name once. I don't think I could spell it. But really what this is we have a spectral classification scheme. And now what we want to do is come up with, we know what to call these things. We decided on a handful of names. And we have a little bit of information about what the names mean about their temperature. What it has to do with their composition is not necessarily clear. But now we want to go back and make more statements about all of the other physical properties of stars and organize them that way. So at the end of today, it would be like I say, hey, I've got a B star, and then you should be able to rattle off no less than 6 bits of information that classifies B stars. And it's really nice because the way you organize it is this 7-dimensional graph. Sounds imposing, but it's just really busy graph. So this stuff is in Chapter 11 of the Essential Cosmic Perspective. Wednesday will, if you guys want to and you're done with Exercise 6 and nobody has any midterm review questions, I'll print them off and bring them in. Bring in Exercise 7. Won't be material covered on the midterm, but that's ages of individual stars. Not lifetimes, but ages. And then the midterm next Friday. There's a study guide on the website, but really, brief answer is that if you imagine taking 3 quizzes and stapling them together, that's going to be the midterm. So lectures 1 through 18, all the way up to what we're finishing today, and then exercises 1 through 6. So spectroscopy, HR diagram stuff. There won't be a quiz on the HR diagram, so I would really take the practice quiz seriously. It's extra long and many questions. So because there's so many multiple choice questions, everybody should bring a Scantron. They're 5 cents a piece at the bookstore. In fact, you should bring more than one Scantron so you could sell them to your peers at exorbitant prices, $5. I don't know. So that's next Friday. And it'll really be 3 quizzes stapled together. A lot of multiple choice, a couple of short answer, maybe a sketch or 2. And I'm waiting back to hear from UW about whether or not they're open on both days, but it still looks like there's an even split in between Tuesday and Monday people, probably. So I'll put an official poll on Canvas. Any questions about that stuff? My midterm more than anything. Yeah. Yeah, and it's a generational thing. So yeah, you need a number 2 pencil to fill it out. So I'll probably have a couple, but it's you feed them through this thing, and it just reads off the reflection of the pencil lead graphite that you fill it in. Yeah. I always tell people if they don't make it, I try to teach this here once or twice a year. If you can remember to remind me, I'm happy to tell you when we do it next time. But yeah, if somebody can't make it, I think one person has actually remembered and taken me up on the offer, but a couple times a year. They also have open houses, and if I also remember, because it's summer, there might be an observing open house with the Jacobson Observatory at UW, and that's pretty cool. It's one of the old Marvin the Martian style, long refractor telescopes where you can look into this comically oversized eyepiece or whatever. But all that stuff, they might have a planetarium show themselves. So if you remind me, I'll try to figure it out. Yeah. Other questions? Okay. Yeah. Yeah, maybe there's something more specific in there. So what were they? They were talking about our planet Jupiter and the sun. So Jupiter you can see with your naked eye. So people in antiquity should have just been able to look up and say, hey, it's Jupiter. Yeah, so that's definitely true. They're compositionally similar. Um, what specifically might be talking about is you don't need a satellite of Jupiter to know the mass of Jupiter if you're really careful. Sorry, let me rephrase that. Is the orbits of the planets tell you the mass of the sun? If you believe in this pure Kepler's third law thing where sun is like hammered into the cosmos and the planets orbit it. But that's not quite true, and it turns out that if the sun has a finite mass and it's not just stapled into the background of the cosmos, is really what will happen is Newton's third law says that even though Jupiter gets swung wildly around, the sun will wobble a little bit, and you can infer the mass of Jupiter through the wobble of the sun. So the mass itself you can tell by observing the sun. And that's the key trick. I don't want to give too much away, but that's how we started detecting planets around other stars. So you can find the mass just by, although it's so much easier just to like sit there and look at Io and Europa and things like that. So, yeah. I suspect that's what the comment was about. So. Yeah, phrase like that, it's a little bit weird. It's like, well, just detect Jupiter by looking at Jupiter, don't we? But yeah, I'll have stuff prepared on Wednesday, but if you guys have questions based on midterm review, bring them. Okay, good. Okay, so this is a lot of material, depending on how much you love stellar astrophysics. It's either super interesting or a little bit sort of at times dry detective story using physics and ideas that we've already figured out and a little bit of new stuff. So we're going to talk about what specifically are main sequence stars, and these are the most sun-like of all of them. For now, main sequence stars are things like our sun that have a core which is burning hydrogen into helium. And in order to get as much information out of them as possible, we actually have to make very clear a distinction in between luminosity and apparent brightness. Luminosity would be like the wattage printed on the surface of a light bulb, and apparent brightness is exactly what it sounds like. We'll get the mass from binary systems, radius through a little bit of thermal physics, which we won't really do. I'll just say thermal physics happened. And then most importantly is the relationships in between them, and this is what's called the HR diagram, where if somebody at the end of this says, main sequence star, light blue, go. You should be able to fill in all of this other information, like what the star's power bill looks like, what its mass is, what its surface temperature is, how big it is. Turns out you can tell all of this stuff. Okay, so this is what we know so far is, it almost looks like the wheels are going to fall off the Newton universal bus where you look out into, it's a very uncharacteristic star field, probably at in the plane of the Milky Way galaxy. And these stars do not look like our stars. They're very red or blue or white or yellow or orange. But we're assuming in all of the evidence nothing is wrong with this model. We can't go there and cut them in half. But we're assuming that all of these things, what we're calling main sequence stars, are hydrogen-fusing stars. So in their core, there are protons bashing into protons and eventually turning into deuterium and then eventually into helium. And as they do that, each individual proton or neutron starts losing mass and emitting tremendous amounts of power in the form of gamma rays. The gamma rays bounce through the radiation zones of these stars, and a million years or so later, they emerge as like a nice, even blackbody spectrum. So the blackbody spectrum and the part of it that we get with our eyes in visible light, we can infer the temperature. So which star is hotter? Yeah, definitely blue star. Blue star is blue star hot. There's nothing else going on that you can detect without a prism. So this is blue star hot, this is red star hot, and if you have already looked at that applet, it's a pretty good correspondence in between the color and the temperature that you can get down to, like, especially for cooler stars, down to like 50, 100 degrees Kelvin. It's kind of crazy. So you have an extra bit of information if you really, really want to work hard, is if you take the light from one of these stars, pass it through a prism, break it apart, and you see the overall color. So this is a star that has a lot of red light, a lot of green light, a lot of blue light. Looks like they're in kind of equal proportion. So this would be kind of a yellowish star. In fact, this is our sun. But then there are these gaps. And the gaps come from the fact that the ideal black body of a stellar surface at some temperature is surrounded by a stellar atmosphere, which is cooler gas, and the black body is emitting all this power, and the cooler gas, if there's hydrogen in the cooler gas, the hydrogen says, hey, these are my favorite wavelengths. There, and there. I will absorb them and then scatter them away so you can't see as much of them. And then there's sodium in the stellar atmosphere. The sodium will say, ooh, sodium wavelengths, and it'll eat it and disperse it. And you can basically tell what's in the stellar atmosphere. Up to the fact that if it's really cool, maybe you don't excite the electronic transitions, or if it's way too hot, maybe you ionize singly or doubly or whatever the gas. But really, this is it. So we can tell that we're totally a recycled star system by the fact that we have all this other nuclear waste, space junk, heavier elements inside of us, which we'll get to when we get to star death. So that's what we know so far, which is quite a lot. And if you have a good telescope and a nice prism, you can actually, learn some information from very, very, very far away, which is kind of crazy. So any questions about that? That was Wednesday. Okay. So now, and this is the cartoon version of so-called Kirchhoff's laws, is I have a hot, dense thing, black body. I have a gas cloud that's getting energized by something. I have only the wavelengths that correspond to its favorite electronic transitions. And if I combine the two, what I get is the cold cloud of gas actually removes its favorite transitions. So you can really think about it as like absorption spectra from the star plus the emission spectra from the atmosphere. If you were to add them all back up, you would get a perfect black body again. Yeah. Could be. Yeah, so some of those might be from last quarter. But I added a couple to these today, so I'll probably update them. Yeah. Okay. So that's a lot. We know temperature, and we know if it's got a stellar atmosphere dusted with some chemical elements. But we're not done, so what else could you possibly ask about stars that's reasonable or unreasonable? I don't really care. Mass, definitely. And that'll always be the first question because we're so good at that, It wasn't just because I really love gravity that I gave you guys 2 exercises on it. It's if you want to know anything about things that are really far away, you really have 2 tools. You have light and gravity. And up until last September, we found out about gravity by light, so it's really light. But absolutely the mass. It's always the first thing you ask, mass. It's always the first thing a theorist does is what's the mass of the thing. First thing an observer would do is what's the spectrum. So what else? Just physical properties. So we know our star is 2 times 10 to the 30th kilograms, or all stars 2 times 10 to the 30th kilograms, maybe not. Our star is 7 times, 10 to the 7th kilograms? Temperature, mass, composition, size. Does it have stuff in its neighborhood? Maybe other stars. We're kind of a solo act. We've got a couple of planets, but really it's us and no other stars close. Yeah, absolutely. Anything else? Density. Yeah, if we find the size and we find the mass, we could calculate the density. And maybe there are some stars that are like superfusers and they're 10 times as dense or something like that. Distance, yeah. In fact, that's going to be kind of a first question before we get to another really important thing. And the last really important physical quantity. So which star's light bills do you want to pay? So we can also ask the total amount of power they're emitting. And in other sciences, I know I'm kind of an astronomy advocate, I guess. But sometimes these questions are really boring in a certain science. Do you guys really care which amoeba weighs more than which other amoeba? Probably not. But remember, we live in a logarithmic science. So there could be monsters out there, right? So there could be a star that's emitting 10 orders of magnitude more power than a different star. Or there could be a star that's 5 billion times less massive than another star. And that would be a real head scratcher. It's what is this superfusing monster doing? So we already know that there's a supermassive black hole that's about 4.3 million times the mass of our sun. So these might not be oh, this one's twice as massive as that one. How boring. which I agree it would be, but we are logarithmic, so these might be crazy. So we don't know. So why are some hotter, brighter? We got that. Mass, that should have been first. Lifetime, I guess we missed. So how long are they going to live? Maybe we don't want to, it certainly appears like they hang around for a while, but there are evidence of guest stars and supernova. Maybe if everything's blowing up after, a million years or so, this bodes poorly for life on Earth. Distance from us, absolutely. Size, got that. Is it a good week to give my dog a bath? You'd have to ask a different class. So this is the first thing that we'll have to worry about, is this is an astronomical image. Which one of these stars is closer? And what makes you think that? Why blue one? Yes, maybe the light's more spread out or something like that if it's closer. What I want you guys to do is appreciate how hard this problem is. And I think somebody asked this, or we ended up there on Wednesday, but when you're seeing a picture like this, you're absolutely not observing the apparent size of the star. It is impossible to image, like, in a single pixel or multiple pixels, the entire disk of the star. Remember, we're talking about the closest star. The closest one is a tangerine that's sitting on Broadway in New York City. So the idea of making a detector that's big enough to have that tangerine, which is 3,000 kilometers away, show up as multiple pixels, it's just, even in this grapefruit model, let alone in the 10 billion times scale bigger, it's completely impossible. So it's just not happening. What you're really seeing is there's so much starlight in that pixel that it kind of saturates them. And the actual star is infinitesimally small. It's never bigger than a pixel. So you're also seeing is the atmosphere probably making this thing jitter a little bit. So the thing I really want to impress upon you guys is this is a hard problem. Yeah. You think the hotter one would be brighter? Okay. What's informing the hotter, brighter idea? Yep. But then do you have some intuition from looking at a toaster oven or something, and as the element gets hotter, it gets brighter? Stuff like that. Okay, so that's a thought. Good. What if it was really huge, though? What if I had a comically oversized light bulb, and it was turned down really low so it was red? Yeah, I can be really assy about this, right? It's a hard problem. So that's exactly what this might be. And this is the problem that astronomers are faced with, even though that's an excellent point, and that's exactly how we'll end up proceeding after we realize that it works until it doesn't with non-main sequence stars, is that, what's actually going on in this image is I photoshopped big and small light bulbs. But the point is that this is a terrestrial analogy, is you don't know if these light bulbs are just intrinsically big, and I got comically oversized light bulbs from the comically oversized light bulb store, or if these look bigger because they're closer, right? So when I look at two stars, I actually don't know if this one appears to be brighter because it's closer and it's putting out less power, or if it's just a giant red star. Maybe there are giant red stars out there. In fact, there are giant red stars out there. So we need to know something. Just taken as it is, there are two things that we don't know. And if you find out one, you can figure out the other one. So the two unknowns that make this problem really, really, really hard is you don't know the intrinsic brightness, which is to say how much power it's actually putting out, and you don't know the distance. And if you can figure out one of those things, you get the other one. Right? So what if I told you that the blue star actually puts out a disturbing amount more power than this red star? Then you can tell me which one's farther away, right? So if the blue star is actually putting out much more power than the red star, then you know that which one's farther. Got to be the blue one, because if it is putting out more power but it looks dimmer, that means it's really far away, right? So the point is you need to know something. And the point is the universe will try to trick us a little bit with non-main sequence stars. So we need distance. And the terminology that we're going to use to talk about this stuff is I guess just as I said in the introduction, is apparent brightness. That's exactly what you think it is. That's what you see from Earth. So if one star looks apparently brighter than the other star, it means that when I look at them, one appears brighter than the other star. I don't know how else to say it. Luminosity is the actual power that the thing's putting out. So that would be like the equivalent of what's stamped on the top of the light bulb, or if you imagine that you had to pay this star's power bill, it would actually come out in some number of kilowatt hours or something like that. That would be a huge number. And now what I can do is I can unravel this issue. So for instance, all of the major stars in Orion, not quite, but they kind of look about the same brightness. So let's just pretend that they're about the same brightness. All the 3 stars in Orion's belt and the end of the sword, and then the knees and shoulders. So let's say that I was able to find the distance, and this was a problem for the ancients, but we've got telescopes in space and really nice optics and 8-meter wide mirrors, so it turns out we can do this now. If I told you that these were the distances to those stars, so you can kind of see the projection of Orion on that. So I found the distance. I found one of the 2 things we'd need to know. Which one do you think has the greatest luminosity? So they all appear the same brightness, but they're all, in actuality, total cartoon. They're, this is not a multiple of the Earth radius. They're 600 light years away or something like that at the farthest. Yeah, so this has got to be the actual brightest. Why does it have to be the actual brightest?
Brighter.
Yes. So the distance is the farthest, but it appears just as bright as all of the other stars. Therefore, it must have the biggest actual power. So then which one has is actually putting out the least amount of power? That's probably safe, right? So it appears just as bright as all the other stars, but it's much closer. Therefore, it's got to be less actual power being put out. So one way or another, we need to know one of the 2 things to figure out the other. So if you told me apparent brightness and luminosity, I could tell the distance. If you told me the distance and the apparent brightness, I could tell you the luminosity. And there's a little bit of math in there, but it's really this, is in order to find the brightness, we've got to find, observe how bright it appears to us, and then adjust for the distance. So if you look at it and you say, looks this bright, and I know the distance, then you can find the luminosity, which is actually, physics. That's not just looking at pretty stars, and that's what we want to know. Okay, yeah.
Stars that are invisible.
So the question is things that only emit in infrared or maybe emit more in ultraviolet. Is that still luminosity? Yeah, but people have to start getting weird about it, and people have to start talking about flux within a certain band or something like that. So for this discussion, you can think about luminosity as the total amount of power that it's draining, and it's putting it out in some, for stars, aside from the brown dwarfs, it's mostly visible. But you can just think about it as the total power it's putting out, and gift me the fact that I'm able to measure it somehow, right? When people really nerd out on some particular type of star, or they only have one instrument at their disposal, they'll talk about something a little bit more refined than that, which absolutely has to do with the type of light it's putting out. They would talk about B-band flux, so for blue, or V-band flux, or infrared flux of some particular type, G, or something like that. But they will let you know exactly what they mean. Yeah, so you can take total luminosity and split it up into some chunks of the electromagnetic spectrum. Absolutely. Yeah. Okay. So we talked about how we couldn't do this, but it turns out that's going to be the first thing that we will use to measure distances. Later we'll come up with other schemes. And, Galileo tried to do this and failed. Aristarchus tried to do this and failed. We live in the age of rocketry and space telescopes. We do this and we totally succeed to a pretty great degree. So the first way of finding distance is just geometry, and that's parallax. So it's totally the camera 1, camera 2 thing. Your close finger appears to shift back and forth. So if you have a closer star against a background of distant stars, it'll look more like it's closer to this star in, I guess that's July. And then 6 months later, you've got this baseline shift of 2 astronomical units, which is not a lot of light years, but if you can observe carefully enough, you can definitely see it. And then this thing will look as if it's shifted to the other side of the far star field. So this works for nearby stars. This works for nearby stars out to maybe like 300 light years or so pretty successfully. And within a 300 light year radius, so the closest star is about 4 light years away. There are a lot of stars there, so you can see quite a few. So we'll do parallax, and you can do it from the ground. There are other ways of doing it, but really the giant drink from the fire hose of parallax is the ipparcos satellite, and we'll talk about space missions and sky telescopes later today. But basically sat there for 4 years just in this big orbit observing the apparent shift of stars. And it got, actually more than that, I think it was like 200,000 distances by parallax, with a resolution of 2 milli-arcseconds. Is that really good? Well, so if you were to hold a finger at arm's length, it would take about 360 of them to kind of tile your way around the circle. So 1, 2, 3, 4, 5, do this, and it takes a couple hundred. So a finger at arm's length is basically a degree. If you were to take your finger at arm's length and you were to cut it into 60 slivers with a razor blade, which is something you also shouldn't do. If you do, don't tell anybody I told you to do it. Then you get an arc minute. If you take one of those slivers and you cut one of those slivers into 60 slivers, so 1/60th of 1/60th of your finger width at arm's length, that is 1 arc second. If you take one of those slivers, the 1/60th of the 1/60th of the finger, and you cut that into 500 pieces, you would get 2 milliarcseconds. So this is really good. A less morbid analogy is to say that ipparcos could probably angularly observe, it has the same angular resolution as reading the last line of this star chart from about Portland or so. It's pretty good. And that's good enough to see stars, right? So there's shift back and forth. So we solved this problem. It was a huge problem for Galileo and the ancients, and it kind of drove them into conniptions about whether or not the Earth is actually moving because you didn't observe parallax. But we totally do this. We totally see parallax. We absolutely have good distances that are just based on like middle school trigonometry to nearby stars. And so we can do this. We can look at the apparent power they put out, so the apparent brightness. We can correlate it to the ipparcos catalog, and we can see the luminosity. And the nicest way of, this is exactly backwards, so the brightest and the dimmest should be flipped. I don't know how that happened. Do you know how that happened? So the pleasant way of describing luminosity is we'll just, do what we started the course by doing and define pleasant units for us. So we'll call them solar luminosities. So 1 L sun would be the same power that the star is putting out. And the brightest stars have about 1 million solar luminosities. So 1 million times brighter than the sun are the brightest stars. And the dimmest stars have about a 10,000th as much power as the sun does. So 1/10 of 1,000th of the sun's total power output. So this is pretty impressive. The difference in between them is that from the brightest to the dimmest stars, there are 10 orders of magnitude. So that's quite a difference. And it will probably tell you something about these guys, the bright ones versus the dim ones, when we get to things like lifetime and the potential age. So the next question we can ask, now we just have like a survey, right? So you have this about 300 light year radius around us that we have parallaxes for, and then we can look at them and we can figure out their luminosities, and then we can also do all the stuff that we could do as of Wednesday, which is look at their spectra and look at their temperature. And now we can answer this question that guys actually already seem like you're ready to get correctly. Is there any relationship in between the thing we know, which is temperature, aka color, and luminosity? So the options are there's absolutely no relationship in between them, and you can have bright red stars or bright blue stars or dim red stars and dim blue stars, like totally uncorrelated. Or the redder stars are intrinsically brighter, so redder stars put out more power, or the bluer stars are intrinsically brighter, put out more power. So many people think A. Red stars are the really luminous ones. People think B, the blue stars are the really luminous ones. No relationship? Okay, one. So you guys are believers in the non-main sequence stars. So for main sequence sun-like stars, it turns out this is absolutely correct, so B is right. Yeah. You tell me. So if these are two main sequence stars, which means that the blue one is actually putting out more power, which one needs to be the farthest? So the blue one might be putting out, like 1,000,000 times more power than the red one. Maybe 100 million times more power. Do you think it's closer or farther? So the apparent closeness of this is just like a trick of the geometry. So imagine that I take two fingers like this, and I just like rotate until they kind of look like they're overlapping along your line of sight. So this apparent closeness, this one could be 1,000 light years farther away. You absolutely don't know. So in fact, if they're both main sequence stars, I know that the blue star is probably much farther away than the red one, because the blue star should be a lot brighter, but it appears about the same brightness, if not dimmer. So that means it's got to be farther away, right? So imagine that I took like a really bright light bulb and a really dim one, and I moved the bright one really far back so that it just didn't appear as bright to you. That's exactly what's going on here. Questions? Make sense? The stellar collision thing is kind of a funny question. Stars don't, as far as people know, there are these kind of theoretical objects where like a neutron star manages to like worm its way into the core of another star. But stellar collisions, they're not billiard balls. They don't like bounce off of each other or anything. So stellar collisions typically take the form of two things get really close, and maybe one's like a big puffy red giant or something, and the other star just pulls by gravity the outer layers of the one star off of it. So they don't like collide. What usually happens is they gravitationally and tidally interact, and one like pulls material off the other one. If that were to happen, then definitely both the star doing the accreting and the star shedding the matter, they would absolutely change all their properties, obviously mass, but then also temperature and rate of fusion and luminosity.
So did you just sort of end up with that essentially where they are smaller stealing?
Well, so if something really, I don't want to call that tame, because 4 times 10 to the 30th kilograms of material like shifting from one star to another star is pretty incredible if you think about it. But people wouldn't really see some like very reasonable in-spiral of two low-mass stars. When people see that happening, it's usually something like a neutron star, which is really dense and compact, or a white dwarf star, pulling material off of a fluffy companion. And it doesn't do something like, I'm just going to get a little hotter, and we're going to agree on a temperature at our median. What happens is it ignites the core of the neutron star, and you get like a supernova. So you can pull material off, and maybe you like have stalled fusion. So you just kind of stopped fusion because you got to carbon, and that's as far as you can go. But then this red giant comes along and starts like putting material on you and says, go. And then fusion starts up again and does so in kind of a cataclysmic way. So those are the things that we see. I think it would be really hard to really clearly image unless it happened to be very close, like two stars in a binary, and then they're just kind of like shuffling, gas back and forth, like a very close binary. It could be things like that. They're actually called, there are other objects called Wolf-Rayet stars that seem to be like just hemorrhaging material out, and maybe they ate something that didn't agree with them, but I don't know. Usually the binary accretion stuff, it ends in explosive tragedy for both of them. So, yeah. Other questions? if you can think of a bizarre scenario, the universe probably has it like somewhere. It's usually the story. Okay. So now we'll go to mass. And you did this, right? So you know exactly how to determine the mass of things. You did this with our star. We did this with planets. How do you determine the mass of a planet, for instance, as per exercise 5? What do you need? So if you want to determine the mass of Saturn, for instance, what do you have to look at? Of what? So you need a thingy, right? So you can kind of think about it as like a mass taster. So with Mars, it was Deimos or Phobos, I forget which. For Jupiter, it was Io, I think. Yeah, you need something orbiting it. So this is almost maybe a problem because the idea of seeing a planet around another star would be kind of rough. So we do need, and we could just like use the equation in exercise 5 like directly out of the can, just realize it gives you Earth masses, and you could turn them into solar masses. Because Kepler's third law doesn't care about whether or not you have fusion going on. It's just Kepler's third law. It tells you something about mass and distance and time. So we did this with Earth. If you want to find the mass of the Earth, figure out how long and at what distance the moon orbits us, some number mass. If you can find two stars, one of which is kind of low mass and the other one is high mass, and they're orbiting each other, then you can also figure out their mass. And in this case, this is a diagram of a really heavy star, high mass star, being orbited by a very light companion. And these people with a nice ground-based telescope, they started their observations in like 1825, and over the course of 85 years, it made a full orbit. So if this is your doctoral dissertation and you were this graduate student, you're like totally screwed. So yeah, 87.7 year period. This is kind of a long one, and maybe you don't want to get, we'll talk about the impatience problem when we talk about weighing galaxies, actually. Like, maybe you don't want to wait the entire 87 years. You could figure out some other way of doing it. But it turns out this is actually like super common, and we're kind of a misanthrope, and the rest of the stellar population, it's basically like a coin flip. So 50% of stars show up in binaries, and you don't have to have the condition where one has a really high mass and the other one has a really low mass, so it seems like one's kind of stapled in place like our sun. If they're about equal masses, they'll orbit each other like this, and you can just go through and modify that formula a little bit. And it's actually really common. And in fact, some of them orbit pretty fast. So here's a nice binary, and this one probably has a lot more mass than that one because it looks like it's staying put. But no problem. So in fact, they're freakishly common, and people have been doing astronomy for a long time. So you can do it with visual binaries. Maybe you actually see them. There are other things called eclipsing binaries where you can't really see the second star because it's pretty dim, but it just makes the other one kind of dim when it passes in front of it. So no problem. So we can find masses in stars, and lots of them. So now we can add that to the correlation, and we've got these two stars about which we knew, kind of tragically little aside from temperature, so hot, cold. And now we know that if they're main sequence stars, this one's actually putting out a lot more power. In fact, probably like, 100 million, 10 million times more power than the red one. So is there any relationship in between color and mass? So the options are there's absolutely no relationship in between color and mass. You can have really light blue stars. You can have really heavy blue stars. You can have really light red stars or heavy red stars. No information. The other option is that the red stars are more massive, or the other option is the blue stars are more massive. So how many people think, A, blue stars are more massive? They're just sluggishly burning through their hydrogen. Blue stars more massive? Any takers? Absolutely no relationship in between them. It was more of an even split. Blue stars. So blue stars are apparently hotter, brighter, and they're more massive. Remember, this is all for like main sequence stuff, and there are going to be funny guys out there like white dwarfs are actually, ironically, most of them are blue, and they'll turn out to be pretty low mass. But for main sequence stars, stars like our sun that are burning hydrogen into helium in their cores, blue ones are heavy. So the blue ones, if you have a blue and a red star, the blue star will basically be in place and the red star will be the one that's being whipped around by the blue star's gravity. Like our sun, so they have a core that's burning hydrogen into helium. Yeah. And I'll say it this way, like from the story of what actually happened historically to do this, is that this was the answer. What I'm telling you is the answer, but 1% of stars acted differently, and it kind of weirded people out. And 1% of stars have a couple of other kind of bizarre properties. So, in fact, a lot of them are the ones that we can see that are a little bit overrepresented. So for 99% of the stars, this is basically okay. 1% are non-main sequencers, and they have to be treated differently, which we'll do after the midterm, because they're the most interesting ones, obviously. Good. Other questions? Yeah. How do you what? Like density-wise. So, for instance, if you went out. Yeah. So you take 1,000 observations, and then 10 of them are like non-main sequence. Right, so it's like the percentage that we see. So if somebody went out and they surveyed 100,000 stars, 1,000 of them would have these funny properties. So, and we presume that, this isn't like unique to astronomy, is we assume that, the millions of things that we've investigated that satisfy Newton's laws, the million and first is probably also okay. So, hundreds of thousands of observations, it seems like very, very stable that 1% of them are non-main sequency. And we actually have a really good theory about what they're doing, or set of theories, which is actually 2 sets of theories. Yeah, good. Other questions? Okay. So this is the mass and luminosity relationship. And really this is something that just trying to kind of get you guys to use like the transitive law of whatever. So do you think that brighter stars are more massive in general, dimmer stars are more massive, no relationship in between them whatsoever? Kind of already answered it. Brighter, more massive? Any dissenting opinions? No. Okay. So we're slowly building this. That's absolutely right. And notice that this is a chart on logarithmic units, so we'll use mass, m star, multiples of the sun's mass. So this is a really nice looking chart, even though this is logarithmic in kind of a goofy way, is that this is where the sun would show up on this mass brightness chart. So 1 solar mass, 1 solar luminosity. And these are a bunch of main sequence stars. So these are guys with like binary companions, so we can find their mass. And then we know their apparent brightness and their distance, so we can find their power. And on the logarithmic scale, it's kind of a cheat. Everything looks nice on a logarithmic scale. It looks like this wonderful straight line, right? So mass goes up, luminosity goes up. And the important part is that the distribution, the spread of these things is really, really, really compact, right? So it seems like if you told me the mass with some degree of precision, I could tell you how much power the thing's putting out. And we're slowly creating what's called the HR diagram. So this is the whole thing. And right now there's, we haven't gotten to lifetime and we haven't gotten to radius yet. But this is the story of main sequence stars, is that if you told me it was a main sequence star and said, look, it's this kind of orangey red, I should be able to tell you all of the following information. So main sequence star, it's kind of orangey red, means it's got a surface temperature of about 3,200 degrees, so that would be the temperature at the photosphere. Because I know the relationship in between color and luminosity, the first thing we did, I could tell you that it's about 1/100th the power that the sun's putting out, so 1/100th of a solar luminosity. Now I know luminosity and I know mass, and I could tell you that it's about 30% the mass of the sun. And then, is that all we got so far? Yeah, that's enough. So we'll get to lifetime and radius in a minute. But this is kind of it. So you tell me one of these things, and I should be able to start spitting out information about the others. Yeah? Okay, so you shouldn't think about this as like what a single star is doing. over the course of its lifetime. The way that you should think about this is somebody hands you a box of stars, and this is what they are. So it's not like this star is heating up or cooling down. So any star that has, its main sequence and has 30% of the sun's mass for its entire main sequence lifetime, which sounds like I'm kind of being cryptic on purpose, but no, it's just because it's hard to talk about star death until you talk about this. If you give me 30% of the sun's mass and you compress it into a star, it will be 3,200 degrees. It will be, 1% of the solar luminosity. It will be an M star. All of that stuff is determined for its entire life. So things aren't like moving up and down the main sequence. They are that. Yeah, for this thing's entire main sequence existence, it'll have ish the temperature. Which I can say because this is a logarithmic graph, the sun is actually getting a little bit hotter as it goes through its lifetime. They do vary a little bit, but something doesn't start its life as an O star and then turn into an M star. So there are mild variations, but it's not, for the main sequence guys, it's basically they start there, they stay there. Yeah. I wouldn't even classify that as a trick question. So that's a very clear question about the apparent brightness versus the luminosity. Yeah. Or brightness from Earth or something. Yeah. So what that really means, because it's important, and we're, I think it would be a trick question if this wasn't astronomy and we had the ability to go out and travel to some star, right? But it's true. I mean, it really is true that we're slave to this planet and we have to observe the brightness from this planet. So if somebody says apparent brightness, they really mean what you get the surface of Earth or just outside of it. And luminosity really is the amount of energy that this thing would have to buy from, the cosmological power company. Good. Okay. So now we can do this and get a little bit of practice. Assume these are all main sequence stars. So maybe, I don't know, a couple of these things aren't, but it's very unlikely. And tell me everything you can about this thing. So this star right here. And take a clean sheet of paper, write it down, try to get as much of the information as possible. That's this one. That. Should a Post-it note or something. Disused beakers full of powder in here. That's great. So, that. So tell me something about this star. Call it star A. Yeah. I totally believe that. So what people very casually call the temperature of the star, which is really the temperature at the photosphere, would be about 4,000 degrees Kelvin. I like that. Anything else? I like many things, actually. Yeah, we'll get there, where this comes from, but yeah, it seems to live more than 100 billion years. That's kind of an interesting statement. So we'll call it lifetime. By reading the HR diagram is greater than 10 to the 11th years. So somewhere here-ish. Yeah. So mass. We'll just round a little bit, call it 0.2 solar masses. What else? There's one more bit of information that's kind of like what we started this whole project with, and it's a little bit like frivolous and arbitrary, but it's helpful because if you say this to somebody, then a stellar astronomer, they should be able to fill in all of that information. Oh yeah, luminosity too. They're there. So we're somewhere here-ish. If we're going to agree with the 0.2 solar masses and say it's this bright, I'll say it's like, yeah. So I'll say it's luminosity. We'll just say the actual power that it's putting out has got to be 0.005 or something like that. Half of 1%, the solar luminosity. Anything else? Yeah, totally not physics. It's something like this. So it's somewhere in the Km border. So maybe it's like a really high K star or it's a really low M star. So it's spectral type. Maybe it's like an M0 or it's a K9 or something like that, K8, something like that. Good.
Are those boundaries?
Yes. And it's totally arbitrary. Yeah, it's like the same frivolous human construct as like, this wavelength of light is blue and this wavelength of light is green. It's like there's a really...
They set up like...
I have no idea. I think where they actually put them is a legacy that goes all the way back to like the early days of the Harvard computers. And I think it's just... I will say this is like astronomy is totally cluttered with all these like very historical legacy things. When we get to the magnitude system, you'll just be like, why have people not changed this? Why is this still haunting us? But I think it's just people way back when they had some very, very thoughtful idea about what they meant when something was a K and something was an M, but it was totally arbitrary. And it really doesn't have anything to do with the equal numbers. In fact, for every O star, there are about 200 M stars or something like that. So the O stars are pretty rare. We just, they put out 1 billion times more power than the M stars, so they get their own class. And they're not equal in terms of the amount of temperature they get. So this is a range of like 10,000, 20,000 degrees. This is a range of like 1,000 degrees, the M stars. So maybe 1,500. It's the last thing we'll talk about is the lifetime, and it's less because something has to win, and you got to think about the mass and the luminosity, because what is the gas tank for a star? A main sequence star is using fusion, so it's how much hydrogen do you have? And you'll notice that one of these things scales really, really strongly, 10 to the minus 5, 10 to the minus 4. 10 orders of magnitude, but as you go from here to here, how many orders of magnitude is that? 2.5. So 60 times the mass of the sun, but putting out 1 million times more power, you're going to burn out faster, right? Because you just don't have as much. The hydrogen to luminosity ratio. Over the course of its lifetime or a day or something like that? Yeah. It starts getting really complicated if you start asking questions like how much hydrogen to helium or other things are in a star like at 1 billion years or 100 million years into its lifetime. But roughly speaking, some people, not me, should be able to tell you like, the O star is 5 million years old. How much of its hydrogen has it burned through? So
O star have approximately the same amount, but burning it
Oh, so the initial condition of a star like this is you're not wrong if you just say like the mass is all hydrogen. And when you look at those spectral lines, it's really like salt in the cake batter. It's like small sprinklings of other elements, at least at the beginning of its lifetime. So, it's not wrong to say, like, look at this O star. It's got 60 times the mass of the sun in hydrogen only, at the beginning of its lifetime. And it's converted some fraction of that to helium at the end of its main sequence lifetime. So you really think about it as like this has, what would that be, like 5% the hydrogen that the O star would have. So at the beginning of their lifetimes, main sequence stars, you could really just say like it's a big ball of hydrogen. And then over the course of fusing towards the end of its lifetime, it starts changing an appreciable fraction of that. Other questions? Is it worth doing another example of reading the HR diagram? Okay. So let's pick star B, and let's make star B this one, right above the orange one. There, if you can't see. So tell me things. So this star B, which is this kind of like blue-white-ish star, and it's assumed to be main sequence, because otherwise we have no idea what's going on. So if it's not main sequence, you can tell its temperature at the surface, and that's it. Yeah, so somewhere here, this is really nice, and this is the version of the HR diagram you'll get for the midterm, just not in color. So you won't need it in color. But yeah, 7,000 degrees surface temperature. Kelvin, anything else? Yep. Yeah. So put a range on it just because you don't really know. A8 would probably be my guess. A8 maybe an F0 or something like that. So somewhere in there. It's right on the AF border, I think. Low A, high F. And who knows where they put the characters on the scale. Good. Anything else? 1.25 solar masses. Trying to trick us with precision. Okay. Good. Yeah, it's somewhere in, 1.5, maybe a little bit more. It's like the pure white one's 1.5, and it's a little bit blue. Maybe you have a range, so 1.5 to 2 solar masses. It's logarithmic, who knows? Yeah, something like that. I'll tell you that wouldn't be wrong in an exam, honestly. So, anything else? Something like that. Yeah, maybe more than that. So it's really hard to get in between the logarithmic graphs. In fact, like 50 would be here-ish, so it's kind of sneaky. But yeah, so 12 to 15, 10 to 15, something like that. And then finally, the thing that we haven't talked about, which is what we'll talk about now, how long is this thing going to live? So about 1 billion years, just by reading and interpreting the HR diagram. So we basically already talked about it. So if you can do that and you can do that quickly, you're in great shape. And honestly, again, in 1920 or something like that, if you took an astronomy course, weeks of your life would be devoted to finding out exactly, with like equations and slide rules, how closely you can get to the actual mass based on, these formulas that interpolate in between points on the main sequence diagram and looking up charts and things like that. But the idea of it is really important, and the idea that for a main sequence star, if you tell me what color it is, I can tell you mass, radius, luminosity, surface temperature, lifetime. So, good. Hertzsprung-Russell diagram. HR diagram is what everybody on Earth calls it. If the guy had a shorter last name like Hertz, it would have been Hertz-Russell diagram. Just too much. Okay. Other questions? Okay, so we have 2 more bits of information, and once we have them, I'll assume you guys know how to read the diagram, and then we'll just give you one that has the information on it. So we can figure out the size of these things, which I think is, of all of them, I think this is kind of a coup, because to look at something and that's so disturbingly far away and say with authority that it's like 4 times the radius of the sun or something like that, I think is pretty impressive. And there's some, thermal physics in it, but the real heart of the matter is this, is which one of these bars is hotter? So that orange color one or that orange color one? It is a trick question. Well, let's see. I don't know if it's a trick. Yeah, they're both the same temperature because they're the same color, right? So they're both equally hot. Okay. But now this is important. Which one is putting out more power in the form of light? So if I wanted to hold my hands over one and heat them with a little bit of radiation, which one would I want to put my hands over to heat? For more heat? So like either 1 centimeter over this one or 1 centimeter over that one. So the thermodynamics answer is that each teeny tiny little piece, so each like square millimeter, is emitting the same number of photons, but this one has more surface area, so it's got more square millimeters. So each part of this thing's surface, its temperature, is emitting light and emitting power, and each part of this is emitting the same amount of power because they're at the same temperature. So for instance, imagine they're iron, like 10 iron atoms at a temperature will be emitting the same number of photons. But what I do is I see more atoms, so this thing has more surface area. And there's an equation that describes it, and that equation is total power in the form of light, which is to say the luminosity, some constant times the radius squared, for a sphere at least, and temperature to the 4th power. The important part is that we actually know 2 of these things, so we can figure out the 3rd one. So we actually know the total amount of power in the form of photons that this thing is putting out, and we know the temperature because we can just look at the color. And if you assume that, it's not a crazy assumption, but if we assume that stars are spheres and there are no QB stars out there or something like that, is that you get a chart that looks like this. So this is right in one way, and it's awful in a different way. So based on the temperature of O stars and their luminosity, you get that they're about 10 times the radius of the sun. By definition, stars like our sun, G stars, are 1 solar radius, and then M stars are about 1/10 of that. So these are correct in size to scale, and they're correct in color. In what way is this probably one of the worst out-of-scale pictures that I've ever shown you in this class? Got something to do with the like the physics of what they're kind of indicating. So this logarithmic scale, stop and really think about what it means. So we have, luminosity here. We've got a M star. It's 1/10,000th of the power that the sun's putting out. Sun's putting out its power. The O star is putting out 1,000,000 times more power than that. They're equally spaced tick marks just because of the scale we chose. Yeah, this is like way off. So if you had an M star in a binary companionship with an O star, do you think you have any chance in hell of seeing the M star? No, it's 10 orders of magnitude dimmer. So I can't, I didn't make this picture, so I'm not going to take blame or credit for it, but one couldn't represent the brightness of the O star, which would be 10 billion times brighter than that on the same picture. So it's out of scale in a new and exciting way that we haven't seen before, is that if you have an O star and there are like 10 M stars around it, no chance you're going to see the M stars. The O star is like, again, 10 billion times brighter. So that's why that's like freakishly out of whack. Okay. So any questions about that? Just we know it, I think, is the important part. Yeah. A constant.
Rotating the orbit of the Earth.
Yeah,
Just the relation of
so the sum number in this formula is a constant of physics that relates the amount of power that something at a temperature emits and a little bit of geometry from the R squared. So if you really want to know, it's the total amount of power in the form of light that something's putting out is the surface area times something called the Stefan-Boltzmann constant times temperature to the fourth power. And in this case, the surface area of the star is 4 pi r squared, which is where the r squared comes from. And the Stefan-Boltzmann constant is this freakishly small number, 10 to the minus 8 in SI units. So it would be like watts per meter squared, Kelvin to the fourth, T to the fourth. But part of it's geometry and part of it's just a constant of thermodynamics. But this is huge and this is pretty big, so the smallness of the Stefan-Boltzmann constant doesn't matter. Although the smallness of this constant is why you don't walk through your life and you radiating power away and get tired because you're at 300 degrees Kelvin or whatever. Other questions? And this we basically already answered, so I think I will fail when I try to trick you this time. I don't know. This is what's going on with star lifetime. Yeah, so this would be like an M star, right? So it doesn't emit a lot of power, but it's not a lot of mass. And this would be like an O star, like a bonfire. So it's got a lot of mass, but it's emitting a lot of power. And it's not entirely clear who wins. So you have more power and more light that you have more mass and you have more power that you're emitting, or you have less mass, but then you're emitting, you're basically emitting light in a very controlled, smaller scale. So who wins? So you got this kind of tortoise and the hare thing going on. Is already stated. So the luminosity of an O star is orders of magnitude bigger, like 10 orders of magnitude bigger than this, while the mass is only 2 orders of magnitude. So overall, the way that you reason through this, and it turns out that this total back of the envelope calculation actually gives you a really good answer. So this would be like an O and this would be like an M. So if you have more mass, that's how you're producing your power through E equals mc squared, conversion of mass to energy via fusion. So more mass means you should be able to burn longer, but then more luminosity means that you're actually emitting more power and you're burning at a faster rate. So the question is which one wins? And if you look at what we've figured out so far, it really looks like luminosity wins. So O stars live a shorter lifetime. And if you want to estimate it, and weirdly, freakishly, this turns out to be pretty good, is you think about your mass as the size of your gas tank. You think about your luminosity as your miles per gallon, And if you divide them, you could basically get like the number of miles you could drive. In this case, it would be the number of years you could burn. So scaling things, one solar mass over one solar luminosity would give you one solar lifetime. For an O-star, maybe like 20 solar masses over 10,000 solar luminosities. You get that it burns for about 2 parts in 1,000 as long as our sun. And then for an M-star, you pull the same stunt. 0.1 solar masses over 10 to the minus 4 solar luminosities, you get that it burns for like 10,000 times longer than the sun. And weirdly, those turn out to be kind of okay. A very...
These guesses are, because there's like, obviously, entire lifetime of the star.
For these, that's absolutely correct. For these, you actually can get pretty good estimates of lifetimes of individual stars through kind of statistical methods and observing clusters of stars. So if you have a whole bunch of stars that were born together and they were gravitationally bound, and you look at them and they're missing a proportion of their stars. So they're missing, like, first they burn through those and first... Exactly, yeah. So it's exactly the same thing you would do if somebody gave you a bunch of samples of radioactive material and you look at the ratio of live stars to missing stars. So you can check the low mass stars that way. These also agree with more detailed nuclear physics calculations. The real question is this. So what is, why has nobody ever seen an M star die? What is 10 to the 11th years, actually? So 10 to the 9th is a billion. 10 to the 10th is 10 billion. 10 to the 11th is 100 billion. How long has the universe been around? 13 billion. Has an M star ever died of natural causes? No. So this is their theoretical lifetime. Who knows, maybe something else is going to happen to them and the universe will come and obliterate them in the Big Crunch or the backwards Big Bang or something like that. But that's their theoretical maximum lifetime based on the amount of material they have to fuse. Maybe they stall out at 50 billion years, who knows. But the important part is, again, mass is like gas tank and luminosity is basically like your mileage. So, and O-stars are the rock stars of the galaxy, short lifetimes, burn brightly. Okay. So if I put radius and lifetime on this, I presume you'd be able to read all of the information off. On the practice quiz, there are a whole bunch of bits of practice. We could do one more if you want, or we could just stop, take a break. Seems like people are HR diagrammed out. Okay. Yeah. It depends on who you are. I think maybe objectively, insofar as they're the least understood. Weirdly, there's a group of these things at the end of their lifetime that kind of break all the rules. And what you'll see when you get to star death is that people kind of group the stars into two groups: the low mass stars, like about our sun, a little bit heavier, and the high mass stars. And they behave really wildly different in terms of how they leave the main sequence and die. And then sitting in the middle, the kind of high but not too high mass stars, as they get older, they don't know whether or not they're low mass stars or high mass stars, and they actually develop instabilities. And so they're variable stars that kind of live in the middle. White stars like Polaris actually is a variable star. And the things that they're doing is actually pretty weird. So if you're a stellar astrophysicist, I think variable stars are kind of where you end up devoting your energies. M stars used to seem pretty boring, but they've got a lot of atmospheric turbulence and stuff like that. Flare stars are M stars, so people actually get excited about those. They can have these things like putting off these giant waves of energy and maybe lighting up their planetary atmospheres and things like that. O-stars observationally would be really difficult to study just because they're few, they don't live for a very long time. At the end of their life, if you study them, you end up being like a pencil and paper theoretical physicist more often than not. At the end of their life, they're like burning silicon into iron and stuff like that, but it happens for 2 days. So a lot of like very greasy nuclear physics questions in the high mass branch. So I don't know. Depends on who you are, I guess. Yeah, so we can get a bit of practice, but I will show you the entire HR diagram the way that you'll see it outside of today's class, and you'll be like, huh? The whole thing has the non-main sequence stars on it. Realize that these guys represent 99% or so, and percent or two out there. And we'll come back and talk about these, but it's kind of hard to find the main sequence only HR diagram. So this is what we're talking about, and everything we talked about today has to do with main sequence stars. Eventually, we'll populate the rest of this. So, and we also haven't talked about age specifically. So you show me a blue star, I can't tell you how old it is. So, questions about that? Yeah. Yes. In fact, if you want to get a really crude estimate of how old a galaxy is, you basically holistically look at its color. And if somebody shows you a galaxy and it's got a lot of like blue light coming from it, or if it looks a little bit bluer, it's still got star formation, it's still got younger stars, it's got O stars. So you know that at least within the last, couple of million years it's been forming stars. Somebody shows you a galaxy that's like really red or yellow, then you can probably say that it hasn't been forming stars in the last 20 million, 50 million, longer time, probably longer. So you do use blue stars as a little bit of a gauge of like the health of galaxies, I guess, if you want to call it that. And there are definitely places out there where there are just no O stars and B stars, so they haven't formed new stars in a while. Yeah. You mean the like when somebody shows you a picture of like a radio image or something like that? Yeah. So for this is like a total integrated power over all wavelengths. And this is, at this point, I think in the 21st century, is the HR diagram has turned into more of a teaching tool than a thing that needs like active research. And the pictures from like Chandra or something like that is they're doing their own thing. They've got like units of flux based on what their particular telescope sees and amount of X-rays that it has coming in per square centimeter and stuff like that. And they really don't interface with the HR diagram, aside from to say that like, oh yeah, we saw this really weird burst coming off of an M star that had some X-rays in it or something like that. Oh, that you would have to, hope that they told you along with the image, and you'll see them. There are keys on the bottom. When we do the telescopes lectures, you'll see it is like, it is people taking credit for like their work and their time and their effort, but they're basically like on the bottom of every single image, it will be like Chandra X-ray Observatory or Hubble Space Telescope Wide Field Imaging Camera, which is, they're trying to tell you as much as you would need to know to figure it out. And if it's not there, then you'd have to like, what took this image? What camera did they use? What wavelengths are they doing? But if it's visible light, nobody messes with visible light. Hopefully, our eyes work perfectly fine in visible light. It's the only thing they do. So, if it's a visible image, hopefully they didn't mess with the colors. And then you could just unambiguously say like, sure. The color key stuff has to do with other wavelengths of light that human eyes just don't do by themselves. So all that stuff, and this is like the thing. This is the thing in stellar astrophysics. So we'll fill in the